So, hello everyone. I'm Zheng from Alibaba Cloud. Today, I'm going to present our work on CStar Gateway, a solution that augments public cloud infrastructure for heterogeneous network function visualization. Let me first start with some background. In the public cloud, network function visualization, or NFV, decoupled network functions such as load balancing led transit router from dedicated hardware, implemented them instead on standard virtual machine. In Alibaba Cloud NFV architecture, we serve each tenant through a VNIC as a tenant traffic endpoint and multiple NF VM from a group to collectively handle tenant traffic, with ECMP distributing the load. This architecture fully reuses the existing cloud infrastructure, inheriting the cloud elasticity and fault tolerance. However, this reuse introduces a fundamental tension. The existing cloud infrastructure is optimized for tenant VM, while NF VM, acting as an intermediate network forwarding node, have fundamentally different resource consumption patterns. We can use the barrier effect to understand this problem. Think of an NFVM as a barrier where the various resources VNIC, session, IO bandwidth, and the CPU are the planks. The amount of water the barrier can hold is determined by the shortest plank. In our product environment, NFVM often cannot accept additional traffic once VNIC or session resources are exhausted, even though CPU and IO may still have abundant capacity. This forces us to provide more NFVM to handle traffic growth, causing costs to increase dramatically. We choose to introduce a CStar Gateway to address the problem. The core idea behind the CStar Gateway is straightforward. Introduce a programmable gateway to address for this shortest plank so that each NFVM can fully utilize all its resources, dramatically reduce both the number and the cost of NFVMs. Before diving into our challenge, let me explain two key concepts. The first is VNIC. In the NFV architecture, each tenant's NF demand is isolated through a dedicated VNIC. Each VNIC carries tenant-specific configuration, including rate limiting, security group, and so on. The vSwitch applies this configuration to enforce access control on incoming traffic, path, job, or meter. The second key conception is the session. To achieve line rate processing, the vSwitch employs a fast and slow path separation design. The first packet of each flow goes through the slow path configuration lookup, creating a session entry that records the VNIC ID and action. Subsequent packets simply match this session and execute the cached action, skipping configuration lookup entry. These two mechanisms work well when serving tenant VM, but in NFVM scenario, serious resource mismatch challenges emerge. We identify 4 critical resource mismatches in production. Mismatch 1, VNIC exhaustion. Our product data shows that across the 3 available zones, NFVM consume an average of over 97 VNIC, compared to only about 2 for tenant VM. Take VPCnet as an example. It must band a dedicated VNIC for each tenant demand to maintain isolation, causing VNIC to quickly hit the vSwitch quota limit. Yet at that point, these VM CPU, memory, and I/O utilization remain extremely low because VPCnet handles lightweight traffic like log upload. The VNIC quota limit is not a hardware bottleneck but an economic design constraint. Smart NIC storage resources are limited. Each server can support only about 4,000 VNIC, and locating more to NF VM would directly reduce tenant VM density and per server revenue. Mismatch 2, session exhaustion. Load balance type NF VM face a similar problem. Microservice access backend storage and IoT device connecting to VPC services generate massive bursts of short-lived concurrent flows, especially get up to 1 million concurrent sessions with second. And filling up the vSwitch session tables. Once sessions are exhausted, new flows are dropped, and even though CPU, memory, and I/O still have much headroom. Our data shows that in a 4 VM load balancing glue, that instance hit 100% session capacity with severe packet loss. Mismatch 3, I/O bandwidth saturated despite idle CPU. Transit router is a poster child for this issue. TR handles high bandwidth in the VPC traffic, high division video cloud sync using stateless L3 forwarding with almost no CPU demand. Our profiling shows that some NF VM nearing peak I/O utilization with only about 6% CPU usage. At T-BPS scale demands scaling VM and I/O balance while paying with idle CPU is economically unsustainable. Mismatch 4, CPU overloaded by heavy heater flow. Although RSS distribute NF traffic across CPU cores, persistent elephant flow can be pinned to a single core, causing packet loss for overflows on that core. This risk is unpredictable. To address these issues, we propose a minimally invasive solution, introduce a Tofino-based stateless gateway, CStar Gateway, between tenant VM and NF VMs. Comparing the architecture and after deployment previously, each NF VM required multiple VNIC. The switch had to maintain a large number of session entry, and complex ECMP consistent hashing was needed. After deploying CStar Gateway, each NF VM need only a single VNIC. Session overhead is aggregated, and the ECMP is migrated from distributed vSwitch to the centralized gateway. Critically, none of these requirements any modification to the vSwitch itself. To address the I/O bandwidth and the CPU resource mismatch, CStar Gateway perform traffic identification and redirection. The gateway identifies all traffic upfront using flow identifier to recognize bandwidth-intensive traffic and elephant flow. Once identified, CStar Gateway performs destination address replacement, redirect these flows to a dedicated processing cluster composed of high-performance FPGA chips. We choose FPGA for these two traffic types because a single FPGA card delivers extremely strong processing performance, make it ideal for band-intensive traffic and elephant flows. However, we do not use FPGA to processing all traffic because FPGA lack elasticity and cannot meet the elastic processing demand of NF traffic, especially stateful NF traffic. Therefore, we retain NF VMs to handle all remaining traffic, giving the entire system both high performance and high elasticity. Now, let me walk through the three core design components in detail. First, we need aggregation. CStar Gateway aggregates all tenant-specific VNIC into just one VNIC per NF VM. Here shows it works. The gateway introduces a logical identifier called a fake or a pseudo VNIC ID, replacing the original vSwitch mapping from VNI and service IP to physical VNIC ID with a mapping to this pseudo VNIC ID. The gateway then encaps the original packet in a Geneva tunnel, carrying the pseudo VNIC ID in the tunnel header, further wrapped in a VXLAN header for transport. On the NF VM side, the VM extracts the pseudo VNIC ID from the Geneva header, looks up to corresponding corresponding tenant configuration, the execute the access control operation that were previously handled by the vSwitch. As a result, the NF VM side vSwitch return only one basic VNIC, completely eliminating the VNIC exhaustion. Second, session aggregation. Through Geneva-Turner encapsulation, multiple flows from different tenants are aggregated into a single Geneva-Turner. Since the vSwitch only sees the outer Geneva 5-tuple, multiple distributed flows consume just one session entry from a vSwitch's perspective. For example, 3 different flows occupy only a single session slot. Fine-grained per tenant access control is migrated into the NF VM, which reuses the vSwitch's fast slow path logic with pseudo-VNIC inner and inner 5-tuple as a session key. We also randomized the Geneva and VXLAN UDP source port on a per flow base with a limited port range, since the UDP destination port must return fixed for Geneva. Modifying the source port, providing a necessary tuple diversity to spread flow evenly across VM cores. Third, FPGA acceleration and elasticity support for I/O intensive, like transit router traffic and unpredictable elephant flows. We designed a hybrid data plan. NF VM monitor real-time per flow packet and byte counters upon detecting an elephant flow. The NF VM sends the flow identifier, the pseudo-VNIC ID and the hash value to the gateway via the control plane. The gateway then redirects subsequent packet to an NF FPGA. Meanwhile, the NF VM's session entry is migrated to the FPGA. The FPGA installs this entry and executes exactly the same action as the NF VM, ensure a seamless handoff. In addition, we migrate ECMP consistent hash from distributed tenant side vSwitch to the centralized CStar Gateway. This simplifies scaling operation from pushing update to hundreds of distributed vSwitch down to updating a few centralized tables in the gateway, thus reduce scaling latency dramatically. With the CStar Gateway, tenant configuration include ACLs and the metering move from the vSwitch into the NF VM. We integrate VNIC level rate limiting and ACL directly into the NF VM's packet processing pipeline. For fast path metering, upon packet arrives in NF VM, first conduct metering before any other logic. Then, if a packet misses the fast path session table, it enters the slow path, match the pseudo-VNIC ID and the inner 5-tuple against the tenant security group. On the NF FPGA side, we also implemented a unified session entry format using a key of pseudo-VNIC plus inner 5-tuple and the pipeline including vSwitch stage and NF stage. Now let's see our evaluation. We selected 3 available zones that had already deployed CStar Gateway and tested average CPU and I/O utilization of all NF VM in these 3 areas before and after the deployment of CStar Gateway. The result shows that after deploying CStar Gateway, the mismatch between the number of VNIC and session resource was resolved. As a result, the traffic handled by NF VM is no longer constrained by the number of VNIC and the session provided by the vSwitch. The single VM can now carry more traffic compared to before, leading to increased CPU and I/O utilization. As can be seen, when CStar Gateway was not in use, the average CPU and I/O utilization of NF VMs were both less than 10%. After after deploying CStar Gateway, CPU and I/O utilization of VM in all 3 ASICs increased by at least 5 times. After deploying CStar Gateway, because some tenant-related configuration like security group and rate limiting is transferred from the vSwitch to the inside of NF VM, this new configuration occupies a very small portion of the NF VM storage space compared to the existing NF logic relay config. As shown in our evaluation, the result clearly shows that each VM still has sufficient resource to store config information, with memory utilization increased by less than 4.3% on average. Most importantly, the cost impact across the 3 ASICs, the number of NFVM was reduced by 80%, 94%, and 91% respectively. Even after accounting for the cost of the CStar Gateway itself, we still have significant cost saving. To summarize, in this work, we introduced the CStar Gateway and designed a set of nested tunnel-based protocols to address resource mismatch problems, including limitation in VNIC and session on the vSwitch to NFVM when building scale NFV product using standard VMs. The solution significantly reduced the cost of deploying NFV system to public cloud based on standard VM without requiring intrusive change to the underlying cloud visualization architecture. It offers a viable path for other cloud service providers seeking to deliver cost-effective cloud-based NFV service. Okay, that's all of my talks. Thank you so much.